Now I know it's after lunch and everyone is not a big fan of chemistry, so I'm going to keep this light and simple, and I'm going to associate chemistry with partying, right? Nobody likes chemistry, everyone likes partying, so I'm going to make that analogy throughout the presentation, so I'll keep you guys awake for the after lunch session. So fallow management, I'm not here to tell you how important it is to spray for fallow management and water conservation, nitrogen, and your economics returns. There's a lot more people more experienced in this room that can tell you a lot more about this subject. But I'm going to use the fallow spray as just a way to hang your hat on spray tank management. And so if you don't manage what's going on in your spray tank, you're not going to get those economic returns, and your spray tank will look something like this. You're either going to get congealed gelatinous material, cottage cheese-like material, crystals, and all sorts of other things happening in the spray tank. Now I'm going to try to help explain this all to you, and to understand this, you really have to go back to the chemistry of how you made these formulations. So I'm going to go over first through spray volume, water hardness, water conditioners, pH, tank mix order, something called the jar test, which you might be familiar with, and then how it all ends, how it ends up on the leaf. So I worked for a group called Actives to Products. So we took actives from a discovery group and put them into products at the end where you sell it in the drum. So it's also a nerdy takeoff on H2O, actives to products, and all the products end up in water, so it kind of works. And we like equations in chemistry, so you've got a science guy working with chemistry to get a new product out there. I'm kind of like the science guy, and I'm kind of like this surfer guy, and you mix surfing with guy with chemistry. It might help explain the rest of my presentation. So let's talk about the party in your spray tank. Now the problem with ECs and SLs is they're the biggest worry in the spray tank, and they're most likely to cause the party in your spray tank to crash. And you do not want the party in your spray tank to crash. You end up cleaning out filters and pumps and the like. So I'm going to teach you how to ensure that your party doesn't crash in your spray tank. First thing we're going to talk about is why you can't take the discovery molecules and just use them as a product. Because acid herbicides, SLs, they don't like to party. The reason they don't like to party is they don't mix with water. The reason they don't mix with water is partially positive and partially negative. And they have to interact with that partial positive and partial negativity of the water in order to dissolve into the spray tank and become the SL formulation. So if you take someone who doesn't like to go to a party, a chemist will give them an attitude adjustment and change their physical properties by changing their chemical properties so that they can party in the spray tank. So we looked at the carboxylic acid group on most acid herbicides, the phosphate group on glyphosate, which is a little odd. Glyphosate's an odd molecule. But picloram and clopyrrolid, it's all the same thing. You're going to alter the carboxylic acid group so it can party in the spray tank. So this is going to be the only equation I'm going to go through, but it's an important one. This is for SLs. When you're creating a soluble liquid formulation, what you're going to do is you're going to take an amine, and you can read this on drum labels when they say a glyphosate or a 2,4-D is an IPA or a DMA. So what we do as a chemist, we take the solid active, we react it with an amine, and you get a salt, something that's partially positive and partially negative, kind of like table salt. You take solid table salt, you can dissolve it in water, it breaks up into its ions and is now a soluble liquid. And so what we're in fact doing is selling a drum full of salt. And this reaction allows the negative ion of the active to interact with the positive part of the water, and the positive part of the amine to react with the other. So it allows it to dissolve into water. The problem is the reaction can go the other way, and what you'll do is get crystals in your spray tank. So this is what we're trying to avoid with soluble liquids in your spray tank. So you're going to throw a party. First thing you got to think about is the venue of where you're going to hold the party. Now if you have when you're choosing the water that goes into your spray tank, you have very little choice of what water you're choosing. Usually you're using bore water, and in some other area you're using rainwater, or maybe a combination of both, or maybe from a stream. So the same with a party. You throw a party, you might have these attractive ions, kind of like those attractive ions in your water, the calcium and magnesium. So these calcium and magnesiums carry a very positive charge, and they can interact with your 2,4-D in this situation and create a half salt. Half salts of 2,4-D aren't very soluble. They'll drop out of the spray tank and start blocking your filters. Now, water can start absorbing some of these ions. The negative part of the water can interact with the positive part of the calcium, magnesium, iron, and suck up a bit of that. So with soft water, it's not such a problem. If you're dealing with something under 200 or 100 ppm, it's relatively soft. As you start getting harder and harder water around 350 ppm, it starts becoming a problem, and it can create these half salts, glyphosate, clopyrrolid, and all those soluble liquids can have this problem, and they crash out. So what we do in quality formulations, they add something called chelators. Chelators cover up those attractive ions so they don't interact with your acid herbicides, and kind of mop them up, cover them up so that charge is no longer interfering. So if you think of throwing your party again, you throw a party on Manly Beach, there's all these uncovered, half-naked ions floating around. People are going to hook up and crash out of your party. So you want to cover them up. So this is what we do in Canada. So you look like this, and no one's going to interact or crash that party. So you want to cover up those attractive ions with chelating agents or water conditioners. Right, now you're going to a party, you need a wingman, and this is another type of chelating agent. AMS, ammonium sulfate. It's glyphosates Wing Man in your spray tank. So what happens is the ammonium sulfate breaks up into a sulfate ion and an ammonium ion. The sulfate ion attracts the magnesium, calcium, and iron, so it doesn't hook up with the glyphosate. Glyphosate wants to hook up with the ammonium ion so it penetrates the leaf better. And so you get no problems with your hard water, and then the proper hookup so it can penetrate the leaf better. Now, if you add too many wingmen to the party, too much AMS, you can cause problems as well. It'll start interacting with the wrong parts of your different acid herbicides, and it'll crash out the party. But so if you're using soft water, I recommend like 1% AMS. Using harder water, 2% AMS. Any more than that, you might start having problems in your spray tank. So you see this at the party. You have Mr. Sulfate distracting the calcium ion in the background, and Mr. Ammonium hooking up with Miss Glyphosate, so at the end of the party, the bright people are crashing out. So that's your glyphosate. Right, so crowd control. Now you don't want to mix too many chemicals in your spray tank or you're going to have problems. It's same with the party. If you invite everyone, the punks, the bikers, the uni students, the college students, and you invite them all into the same party, you're going to have problems. So you want to control the crowd. If you're mixing pure glyphosate, you can go as high concentration as you want in a spray tank without any problems. If you start adding everything else, especially fertilizers and other things like that, you're adding all these attractive ions. They're going to hook up and they're going to crash. This is kind of a little cartoon of what's going on there. Is different ions will actually be attracted to each other, others will be repulsed from each other. And it's a very complex system in the spray tank when you add more and more ions. So you want to keep it simple as possible. The ions that the formulation comes in are almost brother and sister ions. The reason we formulate with those ions is because they want nothing to do with each other. They're just like brother and sisters. They go to a party, they don't want anything to do with each other. They want to see each other at the end of the night maybe and go home or something, but they're not going to hang out with each other at a party. Same with the chemistry you use to develop a formulation. They'll never hook up together in the formulation and crash out. So you'll never have to worry about that. So if you're going to invite people to a party, you want them very similar, very regimented, and they will not cause any crashing in the party. Now, pH. pH is like the alcohol of the party. You know, you want to have a few drinks around the party, get the party moving, but if people start playing drinking games, or if you see the funnel coming out, then you know you're going to have a problem. If you start lowering the pH too much, the acid herbicide will actually revert back to its acid form and crash out of the party. Or, just like at other parties with too much alcohol, it'll find another ion attractive and crash out as well and start blocking up your spray tank. Now it is true, a lot of people talk about glyphosate and the proper pH. If you want the proper pH for glyphosate, you have to hit that 4.5 to 5.8 range. This gives it the proper charge so that it can enter the leaf surface for penetration in the leaf. Now, glyphosate is formulated in such a fashion that it's a liquid, and when you pour it into the spray tank, it automatically hits that pH. A lot of people are like, yeah, but I have really hard water and it's really alkaline, it's like pH 9. In fact, water has very little in it. If you have the hardest water at 1,000 ppm, and so you're, the calcium carbonate, you got your calcium bound up with your chelating agent, so the carbonate changes it to an alkalinity. Now, 1,000 ppm of that is not going to have any influence on the 60,000 ppm of glyphosate you're going to add to your spray tank. It'll dictate the pH, and the pH will fall right to it. I can't show this here. They won't let me take chemicals on a plane for some reason. So I did this in the lab, and here I've got water that's pH 9, you can see here, and I'm adding 1% glyphosate. So this is 1 liter per hectare and 100 liters per hectare spray volume. So it's very low, it's lower than anyone would spray with glyphosate. And you'll notice that the pH goes right down to where it's supposed to be after you add the glyphosate. And it is true that if the pH isn't in the right area, then you will have problems. So what you want to do is, if you're concerned about your pH, check your pH after you add your chemicals. Make sure the pH is correct at the end. A lot of these acidifiers are just causing more problems in the spray tank. As a formulation chemist, I used to get a lot of these quality complaints, and you hear about people adding acidifiers to their spray tank and they're only causing problems. So unless you check your pH after your glyphosate is added, don't bother adding products that are going to lower the pH. Things like Li 700 lower the pH. If you're adding it for other reasons other than an acidifier, then that's fine. But if you're using it as an acidifier, it's not actually needed a lot of the times. So, and then with 2,4-D, it becomes even a bigger problem. 2,4-D has also got great buffering capacity, and if you add your glyphosate, it'll go down around that just under 5. You start adding the 2,4-D, it'll bring it up around 5, and it naturally buffers it. You start taking it lower and lower, these things are going to start crashing out. Crowd control. You want to have crowd control. If you go to a party and it's all crammed in, mosh pit, people are going to hook up and crash out in the party. But it's not only in the spray tank that the party can crash, it's the lineup to get into the party. If you're using a granny pot and pouring 2,4-D on the back of glyphosate, throwing your AMS and dissolving in there, you're going to have problems in the granny pot before it even gets into the bulk of the spray tank. You want to give these ions lots of room to party so they don't interact, they don't hook up, crash up, and fill your filters. I did a lot of work with Statesman, glyphosate, and AMS. So we look at the worst case scenarios and create these charts. So if you want to go 1 liter per hectare, 1 liter per hectare of Statesman, 2% glyphosate, you can go around 60 liters per hectare. And that's the most conservative figure going. A lot of people are like, oh, I've mixed it way higher than that and it was no problem. They might have had softer water. The water conditions might have been warmer. They might have other things in the tank. There's a whole lot of things that can go wrong. And when we do these charts, we look at the worst case scenario. I've went to look at a few instances where farmers was like, I've done the same mix over and over again, and for some reason it crashed out, something's wrong with your product. And we're like, okay, walk me through what happened. Well, it was a cold morning and I half filled the tank and then I threw in the chemicals, then my wife's car broke down. So then I spent an hour fixing that, came back, filled it up with the rest of the water, drove to the furthest paddock, sprayed it out, and the nozzles were blocked. The thing here is time. He was literally using half the spray rate he was before because it was mixing in the spray tank with it half full. And then it was very cold as well, and the additional time to get to the back paddock just all gave the chance for these crystals to form and block the spray tank. So if you are on edge and you start fiddling around with how long you're doing it or the temperatures you're doing it, or maybe you go from a rainwater to a bore water, this might catch you out and you might actually get problems with your spray tank. So if you're throwing a party and it looks like this, I think it's fairly safe to say that no problems are going to happen. If your party looks like this, where you're cramming everything in your spray tank, it looks like you got a bit of alcohol in there, good diversity, you're gonna have problems in your spray tank. And so you want to avoid that. ECs. Now ECs are the oil part of partying, and people are like, well, oil and water don't mix, so what are you doing here? So 2,4-D doesn't dissolve very well in oil either. There are certain things like trichlopyr that dissolve well in oil and they're fine, but the things like 2,4-D, you have to esterify them. So again, you play with the carboxylic acid group, you add a long chain of carbon and hydrogen, and now it makes it more affinable to oil. So you dissolve it in oil. And then you work on that, create that, and you're like, well, oil and water don't mix. How are they going to join the spray tank party? So what we do is add, I'll say this isn't health class here actually, this is an emulsifier. You want to add an emulsifier to the oil, and the emulsifier has an oil-loving tail and a water-loving head. And so when you take this formulation and pour it into the water, it actually breaks up. As a formulation chemist, you look at how beautifully it breaks up because that's how your emulsifiers are working, and it breaks up into these small droplets. And these are like the chaperones at the party. They let the oil in, but they're like, all right, no, there's nothing to see here, that's fine. And they let the oil into the water, and they float around encapsulated by the water. So if you look to the party scenario, these guys are getting into the party, and there's your emulsification droplet. Now, this is where ECs and SLs combine to cause problems. Formulation chemists use anionic surfactants with a negative charge on it so that they repel each other. You create two droplets, they see each other, they're all negative, and they pull apart. So they don't coalesce, creating bigger droplets and oiling out or dropping to the bottom of the spray tank, causing problems. So you get this repulsion. Now the small little ions, whether it comes from the soluble liquids such as potassium salt, DMA, and IPA, will actually interact with this. And depending on the properties of these, you'll cause emulsions to break up. These are different sizes. So a TIPA salt is usually very easy to mix with an EC. It's a big molecule with the same charge in it, so it's got low charge density. Something like a K salt is a really tiny molecule with a high charge density, the same charge. So it can get in amongst this and cause the oil droplets to now interact and collapse, or cause coagulation and cause a mess. So this is why a lot of the K salt glyphosates don't mix as well with a lot of ECs, is you get problems with this ion getting in between there. So at our party, you have your chaperones, they get distracted by attractive ion, a load of oil escapes, they get kicked out of the party, and the oil starts coming out. And if anyone's seen anyone get kicked out of a party, it's never that pretty, it looks like that. So this is what happens typically, something like this or cottage cheese, when an EC starts falling apart, the cross-linking of the emulsifiers causes a gel, and it's a mess. So we're going to take our partying and apply it to adding it to the spray tank. So you probably all see these orders of addition. So this is just explain why we're doing that. First of all, you want to put lots of room to party in there, 2/3 of the spray tank before you add the chemical. Add your chelating agents or water conditioners to make sure you cover up all those attractive ions at the venue of the party. Then you add your granules, flowables, and wettable powders. This is just a physical mixing property. If you have small granules that aren't dissolved, they have a high concentration, and they're going to attract their ions and start breaking up other problems. So you want to just dilute them into the bulk of the spray tank and give it time. Then you want to add your ECs. You'll let these chaperone emulsifiers stack up, and because they are engineered to stack a certain way around the oil droplet. If you add the SLs before that, they start interfering with the stacking, and you get problems with you don't get that good a small emulsion size. After that, you add your SLs like glyphosate and the like, and that will less interact with this. Then you add your wetters. And now the wetters you typically have surfactants. Surfactants will work on surfaces, surface acting, and they'll interact with that stacking of the emulsifiers on the oil droplet. plus they foam. And you don't want all this foam happening while you're putting in these other chemicals, because then you've got chemical foam coming everywhere out of the tank. And then you top it up with water. Now the key is to read the label, but I know a lot of people are adding more to the tank than the label says, and they can, that can cause problems. So it's kind of like, again, back to the party scenario. If your daughter is going to take out a new boy to a party, you want to meet her before you let the two of them loose. So just the same, you want to make sure you meet the parents, I call it. You do a jar test. You use the same water, same temperature, and same concentration. Put it in the jar, give it a shake, leave it for as long as you think is possible for that formulation to be sitting in your spray tank. A lot of people say, 30 minutes. These reactions take time, so if you honestly think you're going to empty that spray tank in 30 minutes, that's fine. I say 5 hours because you never know what's going to happen, and it might be stuck in there for the 5 hours. A lot of people will do it overnight. Do the jar test, leave it overnight. In the morning, how does that look? Crystals, definitely don't mix it in your spray tank. A little bit of cream, no problem. Oil droplets, it's not going to work very well. So those are things to look at. And remember, small problems in the jar test are big problems in the spray tank. Yeah, because you guys are probably thinking this is really ridiculous comparing my spray tank to a house party, because, I mean, it is a little ridiculous because your spray tank has wheels, so it's more like a party bus, really. And so you take that party bus and you spread the party around the neighborhood, and it eventually crashes out on the leaf. And you're all thinking, well, that's the worst wetter adjuvant I've ever seen in my life. And you're probably right, because this is what the emulsifiers, wetters, and adjuvants are designed to do, is to spread out these droplets. They cover more surface area, they disrupt that membrane, and then you can get the actives to get driven in to the plant surface. And as it evaporates, it drives a concentration gradient, so more and more gets in, and eventually it'll crystallize out. Typically it'll crystallize out as its acid form, but if you have things like AMS, you'll get the ammonium glyphosate complex interacting and going into the leaf. With esters and oils, they tend to stay liquid longer, and they also interact with that waxy layer quicker, so you get better penetration. The problem with these oils is they can be very volatile, and you can get drift of the volatilized chemical and cause off-target problems. But that's a completely different issue that we won't cover in this. But all goes well. What you spray should start looking like this. So take-home messages, first of all, read the label. Always read labels. They have a lot of good information. A lot of work goes behind that in the lab to make sure what is said on the label is true. If you're ever in doubt, always go higher spray volumes. A lot of people say, but if I just go 50 liters per hectare, I can get that extra paddock done and I won't have to fill up again. That's when you're likely to have troubles. So always err on higher spray volumes. The more variety you add to a spray tank, the more chance of problems you're going to have. Yeah, it's just plain and simple. And if you are going to go for a larger variety of chemicals, increase your spray volume. pH, glyphosate, and all those chemicals that depend on pH generally hit their target. They're formulated that way, so they don't need anything to adjust those. And if you are concerned about it, take the pH after you've added the chemicals to the formulation. Hardness, it's definitely a problem with ECs and SLs. You can use chelating agents or water conditioners to reduce the charge on those particles, kind of mop them up, and that's always a good idea. And you can also, typically bore water's hard, rainwater's soft. If you're concerned about your bore water, you can get it tested and get a very good analysis of what different species of hard water you have in there. AMS, hard water 2%, soft water 1%, and novel brews, do a jar test, and it'll always save you in the long run, because a little problem in there is easy to deal with as opposed to cleaning out the spray tank. So if you follow those, hopefully you'll keep the party rolling on and you can have some good spraying.